Hello, thank you for clicking on my talk. I will be talking about cosmological measurements of massive light relics. This is joint work with Nick DePorzio, Julian Munoz, and Cora Dvorkin, all from Harvard, from whence I've recently graduated. This is a synthesis of a couple previous papers and some new work that we will hopefully be publishing in a week or two. So to start off with the basic content, it is, I believe, no surprise to the audience that the matter content of the universe is often divided into a minority light known visible sector and a majority dark invisible poorly understood sector. Now, the great success of what's called the CDM paradigm on large-scale observables tells us that most of this dark sector needs to be at least mostly cold and mostly collisionless. But of course, the dark sector is not necessarily monolithic, and some fraction of these dark invisible new particles can be not that. Now, of course, the majority of the big experimental program that has been tasked to look for various types of interactions that these dark particles undergo look for this majority cold collisionless fraction, and well, they should. One might very reasonably ask, why would you care about the minority fraction of dark particles that don't do that? Why care about a small fraction of already poorly understood particles? And that's a fair question. So the reasons I will present is, I guess, first of all, this thing that I'm describing, a subset of invisible feebly interacting particles that are nonetheless not cold and not collisionless, are concretely populated by standard model neutrinos. There are theoretical reasons to look for particles that have similar properties to neutrinos. This will be the archetype that we will be searching for in this talk. But I think in a more general sense, the reason to search for these types of particles is that the small fraction that is not dark, that is not cold and not collisionless, is often allowed to do more interesting things. And because of that, even though they're a small fraction, we stand a chance to detect them. With our rapidly improving data, if we can make a statement, we should make that statement. So, the archetype in question, light but massive relics. These are particles that were in thermal contact with the standard model at the early universe, relativistic at decoupling, but behaving like matter today. Relics that were light but massive. You can split this into two categories. There are neutrinos and there are not neutrinos. Both of these are interesting in their own right. Neutrinos are the piece of the standard model that we really understand the least of. We know that they're massive, but we have not resolved their masses. Not neutrinos are inherently interesting. They are new particles. They definitely mean the existence of new physics, and they're pretty ubiquitous in standard model extensions. I'm essentially describing the light version of a WIMP, more or less. To talk about these not neutrinos sort of as their own category, we will call these new particles lemurs, light but massive relics. And as these pictures indicate, these particles can obey either fermionic or bosonic statistics. That being the archetype of the question, of this talk, the type of data, the observable in question, will be large-scale structure. And this is what we're focusing on, one, because it's really kind of the interesting arena to be looking at in the, you know, these couple years. Our ability to measure these observables and our ability to provide theoretical predictions for these observables has pretty rapidly increased in the last couple years, and we're getting some very interesting data very imminently. And of course, we're interested in large-scale structure for this particular type of particle because it carries the information that we need. Large-scale structure carries information on modes that the CMB does not carry. So, the big picture of this is, of course, this free streaming story, very analogous to the neutrino one. Cold dark matter clusters at all scales. Lemurs, neutrinos, and lemurs do not, because they decoupled while relativistic. They have some pretty significant thermality, and that translates to a free streaming scale beyond which they cannot cluster. And that impedes galaxy formation in a scale-dependent way. This observable effect is independent of any present-day particle interactions, and I think that bears mentioning because, like neutrinos, the main properties of these light relic particles are that they're light and they interact very feebly, and this is really the type of thing that traditional particle experiments have the toughest time looking for. So consequently, it's kind of the arena where cosmological data carries the greatest power. So, what are these particles in a little bit more detail? For the purposes of this talk, a relic is characterized by its mass, temperature, and thermalized degrees of freedom. We will assume that they are stable and negligibly self-interacting. Now, this is a pretty model-independent, pragmatic sort of picture for these light relics. But I can tell you, for instance, that these parameters that I've laid out tell you some things about the underlying particle physics. For instance, the present-day temperature tells you something about the time in the universe in which these particles decoupled. The earlier that these particles decoupled, the more times the standard model thermal bath heated up since then, as heavier non-stable degrees of freedom annihilated into the bath, and therefore the colder these relics are compared to the photons in the present day. So because we know of a finite amount of degrees of freedom in the standard model, for minimum extensions to the standard model, these relics predict a minimum temperature. This is about a Kelvin. So if we find something that's colder than that, either some non-standard thermal evolution happened, or there are even more particles than this relic, in addition to the standard model. So these particles, they decouple while relativistic, and while relativistic, they contribute to the radiation energy budget of the universe. This contribution is typically parameterized by this N effective parameter, delta N effective, effective number of neutrinos, and traditionally this has been our main probe to look for the presence of these light degrees of freedom. For instance, the newest iteration of Planck data sets constraints on N effective, on the amount of extra radiation energy the universe can tolerate, the data can tolerate, and this sets some fairly weighty constraints on the maximum temperature for instance, neutrino like wild fermions. But in our picture, we will also be considering the mass of these particles. And what these masses, the presence of non-zero masses for these particles bring are these free streaming scales. There is a scale beyond which these particles do not clump. There is a scale above which they do. And the scale is proportional to the mass over temperature. And finally, because these particles, by assumption, are matter today, they contribute, they have some present-day abundance that is generically some very small fraction of what we observe as the present-day matter abundance. So these are sort of the observational quantities that these relics these relics contribute to. These are the things that govern the signatures that we will eventually observe. So what are these signatures, I guess? So we'd like to learn about these particles via large-scale structure, and the thing that we actually observe there are galaxies, and galaxies are biased tracers of matter. In the traditional picture, at least, galaxies are biased tracers of matter, and matter is cerium, baryons, and in our case, neutrinos and lemurs. So all these things. Structure formation is kind of like a fight between things that cluster and things that expand. And neutrinos and lemurs influence the story, they alter the story because They're matter, but they don't cluster like matter, like I alluded to before. There's a scale beyond which they don't cluster. So really the first amendment to this traditional story is galaxies are bias tracers of only the clustering matter. Galaxies are made up of CDM and baryons. They're not made up of neutrinos. So if you inject these light degrees of freedoms into your universe, if you have relics, if you have neutrinos, then there is a fraction of what you observe as your matter abundance that's not helping you make galaxies. But it's actually, slightly worse than that, because it's not just that they're not helping you make galaxies, they're actively contributing to the expansion of the universe because they're matter during matter domination. So they're actively sort of tearing your galaxies apart at these scales. So the CDM baryon fluctuations themselves will be suppressed relative, in some scale dependent way. And this effect, you can kind of coarsely describe it as with a scale and an amplitude. The scale given by the free streaming scale and the amplitude being set by the abundance. And the fact that there are sort of two aspects to this signature, the scale and the amplitude, means that we can disentangle the different effects of masses and temperatures. We can distinguish two relics with the different masses versus two relics with different temperatures. That's what I'm trying to say. So let's actually try to distinguish these things. So the datasets that we'll consider are the Planck 2018 temperature polarization lensing, the CFHT lens weak lensing survey, and the broadband full shape data provided by BOSS data release 12. So this will be like an MCMC Markov chain Monte Carlo analysis where we vary sort of the standard parameters, neutrino masses, and these new lemur parameters, considering a range of different types of particles. So, are there lemurs in our universe? Well, what we have found is no, or honestly, you wouldn't be hearing about it like this. We have not found any evidence for lemurs, but what we can do is, of course, set constraints. These are constraints for the maximum temperature of a relic of fixed masses. These relics towards the low mass end, essentially, these constraints essentially trace out an effective constraints. On the high mass end, we see that our constraints kind of plateau as these high mass, low temperature relics essentially act more and more like cold dark matter. If we restrict to the minimum temperature 1 Kelvin, 0.91 Kelvin case, for these different types of particles, we can see that we don't place constraints on this scalar case. It has fewer degrees of freedom, a comparatively smaller observational effect, but for the other types of particles that we consider, we do place some pretty non-trivial constraints on the maximum mass that the data tolerates for these types of minimum temperature particles. I guess I should note that, looking at the previous slide, you see that universally higher temperature relics are easier to constrain, which is pretty unsurprising. But this means that the minimum temperature case is really the most conservative one, while fermions of higher temperature are easier to constrain. So this is really a pretty conservative thing. We can look for pretty much all of these wild fermions, and all of them will be constrained at about the 2.3 EV masses. As a quick comparison to previously available constraints on similar types of particles, as far as we can tell, we are the only constraints for the different other types of particles, vectors, and Dirac fermions that we know of. And for the most commonly searched for neutrino-like wild fermions, we present the strongest constraints by a non-trivial amount, quite a bit due to our new access to the broadband full shape data as an improvement from the sort of traditional BAO only approach. So as a quick sell to someone who might be more motivated by particle physics specific models, one of the things that you might be interested in searching for are light gravitinos that arise in gauge-mediated SUSY breaking scenarios. These particles, their masses, tell you something about the SUSY breaking scale, and they're expected to be very cold, have decoupled very early in the universe indeed. And even though these are actually spin-3 half particles, because this is that effective degree of freedom thing, because they decoupled while relativistic, only 2 of the 4 degrees of freedom that a spin-3 half particle has were thermally populated. So as far as cosmological imprint go, they are equivalent to a wild fermion. So we can constrain those. Our constraints on the gravitino mass, 2.3 eV or so, gives us constraints on the SUSY breaking scale at 70 TeV or so. And this is pretty significant because, you know, tens, hundreds of TeV, is the type of energy scale that, you know, futuristic colliders are aiming for. And this is something that we can say like right now with presently available cosmological data. And cosmology is especially complementary to particle physics approaches in this type of regime because we provide upper bounds on the scales of new physics rather than lower bounds as are typically seen in, you know, particle physics types of constraints. So to wrap everything up, dark sectors are worth studying in whole and in part. I think that's kind of the marketing takeaway that I'd like to give, just because a type of particle might just be a fraction of the dark matter content doesn't mean it's not worth searching for, doesn't mean we don't have anything interesting to say. There are reasons to care about lemurs, and if you do, cosmological data kind of corners the market on saying things about lemurs, and we can say some pretty non-trivial things now, and with better and better data coming soon, we will hopefully push closer and closer towards a discovery. It's a very optimistic thing to say, but that's what I'm going to end on. Please enjoy this lovely illustration by my very soon-to-be sister-in-law of galactic lemurs. Thank you.